Beneath the streets of Philadelphia, Boston, and New York, there are water pipes made of wood. Not iron, not clay, wood. Hollowed-out tree trunks, bored end to end, joined with iron bands and buried underground. Some laid in the 1700s, and some, 200 years later, still had water running through them when crews dug them up. Before iron foundries could produce pipe at scale, America had no choice. If a city needed water, someone had to find a straight log, bore out the center, and bury it, mile after mile. This is the story of how colonial America built its first water systems from trees. How men with hand-operated boring machines carved holes through solid wood, 1 foot at a time. How cities gambled their survival on lumber buried in the mud. And how, centuries later, construction crews still pull these pipes from the ground, the wood dark as coffee, the boreholes still perfectly round, water stains still visible on the grain. The men who made these pipes are long forgotten, but beneath your feet, in the oldest American cities, their work remains. Let me take you underground. To understand why anyone would bury wooden pipes, you need to understand what colonial cities actually looked like, and more importantly, what they smelled like. Philadelphia in 1790 was the largest city in America. Roughly 40,000 people packed into a few square miles along the Delaware River. And those 40,000 people had no centralized water supply. Think about that for a moment. 40,000 people. No running water, no faucets, no hydrants. Nothing that we would recognize as infrastructure. Every drop of water for drinking, cooking, washing, and fighting fires came from one of 3 sources: private wells, public pumps, or the rivers themselves. The wells were dug wherever someone could afford to dig them. Some went down 30 feet, some went down 60. The diggers would lower themselves into the shaft with a rope and bucket, chipping through clay and rock with hand tools until they hit the water table. Then they would line the walls with stone or brick, install a pump or winch at the surface, and call it done. The work was dangerous. The shafts were narrow. Men died when walls collapsed, burying them under tons of mud and stone. They died when bad air accumulated at the bottom of deep wells, suffocating before anyone could pull them out. They died from falls, from equipment failures, from the dozen ways that digging a hole in the ground can kill you. And after all that danger, after all that labor, the wells they dug were contaminated before the first bucket came up. Every single one of these wells sat within spitting distance of an outhouse, a stable, or a tannery dumping waste into the soil. You have to understand how these cities were laid out. Space was precious. Land within the settled area cost money. Buildings crowded against each other, sharing walls, their roofs nearly touching across narrow alleys. The outhouse for one home might be 15 feet from the well for the next. The stable where horses deposited manure all day long might share a property line with the neighbor's water source. The soil did not care about property lines. Water seeped through it in all directions, carrying whatever it dissolved along the way. What went into the ground in one place came out in another. The well water in colonial Philadelphia was not water in any sense we would recognize today. It was a solution of everything that had leached into the ground around it. You can imagine what that water tasted like. You can imagine what floated in it when you held a glass up to the light. Particles of matter that you did not want to think about. A smell that made you hold your breath while you drank. A film on the surface that broke when you touched it. People drank this water because they had no choice. They gave it to their children. They cooked their food in it. They washed their wounds with it. And when they got sick, they often did not connect their illness to the water they consumed. The public pumps were no better. They drew from the same groundwater, contaminated by the same sources. A public pump might serve dozens of families, all of them drawing from a well that sat downstream from every privy and cesspit in the neighborhood. During dry summers, the pumps often ran dry completely. The water table would drop below the well bottom, and suddenly an entire neighborhood had nothing. Families would walk miles to find a working pump, waiting in line for hours, fighting over position. The rivers were worse still. By the late 1700s, the Delaware and Schuylkill were open sewers. Slaughterhouses lined the banks, dumping offal directly into the current. The butchers threw entrails and bones into the water because there was nowhere else for them to go. Tanneries poured the chemicals they used to treat hides straight into the flow. Arsenic and lime and sulfuric acid, all of it mixing with the water that flowed downstream to the city. Chamber pots emptied from upper windows into gutters that drained to the waterfront. Dead animals floated past. Human waste clouded the shallows. The smell on a hot summer day was enough to make your eyes water from a block away. And people drew drinking water from these rivers. They filled buckets and carried them home. They gave this water to their children. They had no choice. When the wells ran dry, when the pumps failed, the river was all that remained. The result was predictable. Disease swept through these cities with terrifying regularity. Yellow fever arrived in Philadelphia in the summer of 1793. By August, people were dying faster than anyone could count them. The symptoms were horrific. Fever and chills that came on suddenly, without warning. Muscle pains so severe that patients screamed when touched. Then the bleeding began. From the gums, from the nose, from the bowels. The skin turned yellow as the liver failed. And then death, usually within a week of the first symptoms. Roughly 5,000 people died in Philadelphia that summer and fall. That's 1 in every 8 residents. Bodies piled in the streets faster than anyone could bury them. Entire families were wiped out. Houses stood empty, their occupants all dead. No one willing to enter and remove the corpses. The mayor stayed at his post, organizing what response he could. The federal government fled the city entirely, Congress and the president relocating to avoid the plague. Businesses closed, churches emptied. The streets fell silent, except for the death carts rumbling over cobblestones, collecting bodies for mass burial. And everyone knew, though nobody could prove it scientifically yet, that the water had something to do with it. The fever struck hardest in the low-lying neighborhoods near the rivers. It spread along the routes where people shared water sources. Something in the water was killing people, even if no one could say exactly what. But disease was not the only problem. Fire was perhaps worse. Colonial cities were tinderboxes waiting to ignite. Wooden buildings packed shoulder to shoulder, sharing walls, their roofs nearly touching across narrow alleys. Open hearths in every home, fires burning constantly for cooking and heat. Candles and oil lamps for light, their flames flickering inches from wooden beams and fabric curtains. One spark in the wrong place, and entire blocks vanished. The fires moved faster than people could run. A blaze that started in a kitchen could engulf a building in minutes. The flames would leap to the neighboring structure, then the next, then the next. Radiant heat alone could ignite buildings across an alley, the fire jumping without physical contact. By the time anyone organized a response, a dozen buildings might already be burning. When fire broke out, the only defense was a bucket brigade. Men formed lines from the nearest pump or river, passing leather buckets hand to hand, throwing water on the flames 1 gallon at a time. Picture what that looked like. A building fully engulfed, flames shooting from every window, the heat so intense you could not approach within 50 feet, and a line of exhausted men passing buckets that held perhaps 3 gallons each, throwing that water toward flames that laughed at such pitiful efforts. It rarely worked. By the time the brigade formed, the fire had usually spread beyond control. The best you could hope for was to save the buildings downwind, to create a fire break by soaking roofs that hadn't caught yet, to pray the wind did not shift. Boston learned this lesson in 1760, when a fire destroyed over 400 buildings in the waterfront district. Warehouses full of goods, homes where families had lived for generations, churches older than anyone alive. All of it gone in a single night, because there was no water available to fight the flames. New York learned it repeatedly throughout the colonial period. Great fires swept through the city in 1741, in 1776, in 1835. Each time the story was the same: flames spreading faster than anyone could respond, bucket brigades overwhelmed, hundreds of buildings lost. Philadelphia lived in constant fear of the same fate. Every summer brought the terror of fire season. Every dry spell raised the risk. Every building that went up in flames reminded everyone that the entire city could follow. The solution was obvious. Cities needed water delivered under pressure, available at every corner, ready to fight fires and supply homes without depending on contaminated wells. The problem was how to deliver it. In Europe, some cities had begun building water systems using cast iron pipes. London had iron mains by the late 1600s. Paris was expanding its network. The technology existed. The methods were known. But America had no iron industry capable of producing pipe at scale. The foundries that existed were small operations, making simple castings for local use, pots and pans, basic hardware, tools and implements. A continuous iron pipe, 8 inches in diameter and 12 feet long, was beyond their capability. The furnaces were not hot enough. The molds were not precise enough. The skilled workers who knew how to cast such pieces did not exist in sufficient numbers. Importing iron from England was theoretically possible, but economically absurd. A single 12-foot section of cast iron pipe might weigh several hundred pounds. Shipping it across the Atlantic would cost more than the pipe itself. Then hauling it from the docks through unpaved streets to wherever it needed to be buried would cost more still. A city that needed 20 miles of water mains would bankrupt itself trying to import enough iron to lay them. So American engineers looked at what they had, and what they had was wood. Specifically, they had forests full of straight-grained trees, perfectly suited for boring. White pine from the northern states, growing tall and true in the cold climate. Elm from the mid-Atlantic, with its interlocking grain that resisted splitting. Hemlock and spruce from wherever they grew thick, their trunks reaching diameters of 2 feet or more. The idea was simple in concept. Take a log, 12 to 15 feet long. Bore a hole through the center, 3 to 6 inches in diameter. Join the logs end to end. Bury them underground. Let gravity do the rest. Simple in concept, brutally difficult in execution. If you're finding this useful, consider subscribing. I cover the forgotten infrastructure and lost trades that built America every week. Now let me show you how they actually made these pipes. The process began in the forest, and it began with selection. Not every tree could become a water pipe. You needed specific qualities that only certain specimens possessed. First, diameter. The trunk had to be at least 12 inches across at the point where you would bore it, preferably larger. A pipe with walls less than 3 inches thick would be too weak to withstand the pressure of water flowing through it. That meant starting with logs substantial enough to leave adequate wood around the borehole. Second, straightness. The grain had to run true from one end to the other, following the length of the log without twisting or spiraling. Twisted grain made boring nearly impossible. The auger would follow the grain rather than the center line, emerging from the side of the log instead of the far end. A log with twisted grain was firewood, nothing more. Third, the absence of major knots. Every branch that grew from the trunk left a knot in the wood, a dense mass of grain running perpendicular to the main flow. Boring through a knot was slow, difficult work that dulled augers and risked breaking them entirely. Too many knots, and the log was useless. Fourth, species. Different woods had different properties, and those properties determined how well the finished pipe would perform. Elm was the preferred species in the mid-Atlantic states. American elm has grain that runs tight and interlocking, fibers woven together in a pattern that makes the wood nearly impossible to split. That same quality makes it resist water penetration. You could submerge elm in water indefinitely, and the fibers would swell to seal any gaps, becoming more watertight over time. Bury elm in saturated ground, where the water table keeps it constantly wet, and it will outlast iron. White pine was common in New England. The grain is softer, much easier to bore, allowing workers to produce pipes faster with less effort. But pine is more prone to decay if exposed to air. Pine pipes needed to stay wet constantly. Let them dry out during a drought or a system shutdown, and they would crack and split within a few years. Hemlock, spruce, and even cedar were used in certain regions, depending on what the local forests provided. Each species had its quirks. Each required slightly different handling. The men who selected trees for boring learned these differences through experience, judging a standing tree by its bark and shape. Once a suitable tree was felled and trimmed of branches, the log was transported to a boring yard. In the early years, this meant dragging it with oxen or horses over whatever roads existed. A team of oxen could move a log weighing half a ton, but slowly, perhaps a mile in an hour over rough ground. Later, as cities built permanent waterworks, the boring happened on-site at central facilities. Logs arrived by cart from the surrounding forests, stockpiled in yards where they would season briefly before processing. The boring machine itself was a study in mechanical ingenuity developed over decades of trial and error. Picture a horizontal lathe, but designed for logs instead of metal. Two heavy wooden supports stood at either end of a long bed, one fixed in place, one sliding on rails to accommodate logs of different lengths. The log was lifted into position using block and tackle, then secured with clamps or dogs that bit into the wood. It had to be absolutely centered, aligned precisely with the axis of the boring auger. Any misalignment would result in an off-center hole, thicker walls on one side, thinner on the other. The auger itself was a fearsome tool. A spiral of iron, 3 to 6 inches in diameter, with a cutting edge at the business end and a socket for attachment at the other. The spiral channels directed shavings backward as the auger advanced, clearing the borehole of debris. The auger was turned by hand. There were no engines, no motors, no power sources except human muscle. 2 men, sometimes 4, worked massive wooden crank handles attached to a geared mechanism that rotated the auger. The gears provided mechanical advantage, allowing the men to apply tremendous torque to the cutting edge, but they also slowed the rotation. The auger might complete 1 revolution every few seconds. 1 inch of progress might take 10 minutes of continuous cranking. The men leaned into the handles, pushing with their legs, throwing their weight against the resistance of wood fibers parting before the auger's edge. Their arms burned, their backs ached. Sweat soaked through their clothes, even in cold weather. Boring a 12-foot log could take an entire day. 8 hours or more of constant labor, rotating positions every few minutes to prevent exhaustion, stopping only to sharpen the auger when the edge grew dull. The process required constant attention beyond mere physical effort. If the auger drifted off center, following a line of grain or deflecting around a hidden knot, you would end up with a pipe whose walls were too thin on one side. The men at the cranks had to feel the resistance change, sense when the auger was wandering, adjust their pressure and angle to bring it back on course. Thin walls meant weak spots. Weak spots meant bursts. A pipe that burst underground would flood the trench, undermine the street above, possibly collapse whatever structure stood over it. So the borers worked by feel as much as by force. their hands sensitive to every change in resistance. The shavings emerged from the back of the auger in a continuous spiral, curling out of the borehole in long ribbons of fresh-cut wood. The smell was extraordinary, sharp and clean, the scent of sap and cellulose released as the fibers parted. Someone had to clear these shavings constantly to prevent jamming. It was usually the youngest worker on the crew, a boy of 12 or 14, crouched beside the machine, pulling handfuls of wet sawdust free while the auger spun inches from his fingers. This was dangerous work. The auger had no guard, no safety mechanism. A sleeve caught in the spiral, a hand that slipped too close, and the boy would be pulled into the machine. Injuries were common. Deaths were not unknown. The historical records mention workers losing fingers, hands, sometimes arms, to the boring machines. But the work continued. The demand for pipes was insatiable, and there was no other way to produce them. When the auger emerged from the far end of the log, the pipe was pulled from the machine and inspected. Workers examined the borehole visually, looking for irregularities, for spots where the auger had wandered. Then they tested it under pressure. They would seal one end with a wooden plug, connect the other to a hand pump, and drive water through the borehole with increasing force. A good pipe held pressure without complaint. A defective pipe bulged at its thin spots, leaked around hidden flaws, sometimes burst dramatically. A defective pipe was scrapped. There was no fixing it. The log that had taken a day to bore became firewood in an instant if it failed inspection. Good pipes were set aside for joining. If you want to see more about the forgotten infrastructure beneath American cities, hit that subscribe button. I post new content regularly on the trades and systems that built this country. The joining process was as critical as the boring itself. A water system is only as strong as its weakest connection, and wooden pipes presented unique challenges. The most common method used tapered ends. After boring, workers would shape the ends of each pipe using specialized tools. One end was shaved to a point, like a blunt spear, the diameter narrowing over the last 6 to 12 inches. The other end was reamed out slightly wider, creating a socket that matched the taper of the adjacent pipe. The tapered end of one pipe would jam into the receiving end of the next, male into female, creating a friction fit. Workers drove the pipes together using heavy wooden mallets, pounding until the taper seated firmly. When the wood got wet, it swelled. The tapered joints grew even tighter, the fibers expanding against each other, sealing gaps that might have existed when the joint was first made. This was intentional. The system was designed to improve over time. Iron bands reinforced these joints against separation. A blacksmith would forge rings sized exactly to the outer diameter of the joint, heavy bands of iron an inch wide and a quarter-inch thick. While the bands were still warm from the forge, workers would drive them onto the joint using sledgehammers, forcing the iron over the bulge where the two pipes met. As the iron cooled, it contracted. The band squeezed the joint together with tremendous force, preventing the tapered end from backing out under pressure. Some systems used a different approach entirely. Instead of tapered ends, they cut both ends of each pipe square and connected them with iron sleeves. The sleeve was a cylinder of cast iron, slightly larger in diameter than the pipes, long enough to bridge the gap between them. Workers would slide the sleeve over the junction, then pack the space with oakum and tar. Neither method was perfect. Joints were always the weak point. A shift in the soil from settling or erosion could pull pipes apart. A heavy cart rolling overhead could push them out of alignment. Frost heave during a cold winter could lift one pipe higher than its neighbor. Any of these could separate a joint and send water gushing into the surrounding earth. The break might be small, a trickle that took months to undermine the street above. Or it might be catastrophic, a burst that flooded basements and collapsed foundations. But the alternative was no water at all. Philadelphia became the testing ground for wooden water pipes on a municipal scale. In 1799, the city authorized construction of the Center Square Waterworks, designed by Benjamin Henry Latrobe. Latrobe was not a native Philadelphian. He had immigrated from England, where he had studied engineering and architecture, where he had seen the water systems of London. He knew what was possible. He also knew what was practical given American resources. His plan was ambitious. He would dam a section of the Schuylkill River, collect water in a settling basin, then pump it to a raised reservoir in the center of the city. From there, gravity would distribute water through a network of wooden mains to every neighborhood. The pumping would be done by steam engines, two massive Boulton and Watt machines imported from England at staggering expense. These engines represented the cutting edge of technology. The pipes, however, would be local. Thousands of feet of bored logs laid in trenches across the city. Construction began in 1799 and took 2 years of continuous labor. The boring operation alone employed dozens of men, working in shifts to produce enough pipe. The yards ran from dawn to dusk. Finished pipes stacked up in rows, waiting for the trenching crews. The trenching was brutal work. Men with picks and shovels dug through unpaved streets, through yards and gardens, through whatever lay in the path of the planned mains. The trenches had to be deep enough to protect the pipes from frost, 3 feet or more. The diggers encountered everything: buried foundations from earlier buildings, old wells that had been filled and forgotten, rock outcrops that had to be broken with hammers and chisels, the corpses of horses and dogs buried where they had fallen. Behind the diggers came the pipe layers. They lowered each section into the trench, aligned it with the previous section, drove the tapered joints together, and fitted the iron bands. Then they tested for leaks, pressurizing each joint before moving on. Behind the pipe layers came the backfill crews. They shoveled the excavated dirt back into the trenches, tamping it down in layers, restoring the street surface as best they could. Hundreds of men worked on the system at its peak: laborers and craftsmen, engineers and supervisors, blacksmiths forging bands, and carpenters building pump housings. By 1801, water flowed through wooden mains to hydrants and fountains across Philadelphia. For the first time in the city's history, clean water was available without walking to a river or pumping from a contaminated well. The system was far from perfect. The wooden pipes leaked at nearly every joint. The steam engines broke down regularly. The reservoir sometimes ran dry during droughts. But it worked. People could open a hydrant and drink. Firefighters could connect their hoses and fight blazes with pressure instead of buckets. And its success inspired other cities to attempt similar projects. New York began laying wooden mains in the early 1800s. Boston followed. Smaller cities and towns throughout the Northeast copied the technology, each one boring its own logs, burying its own pipes. For roughly 40 years, from the 1790s through the 1830s, wooden pipes were the standard in American water infrastructure. Tens of thousands of feet of bored logs ran beneath American streets. And throughout those 40 years, the same questions haunted every engineer. Would the pipes last? Would the wood rot? Would the system outlive the men who built it? Let me tell you what happened. If this is the kind of content you want more of, the forgotten stories beneath the surface, subscribe, and I will keep bringing them to you. The wooden water systems faced challenges their designers could not have fully anticipated. Fire was perhaps the greatest irony. The systems designed to fight fire were themselves constantly threatened by it. Wooden mains ran beneath wooden streets, surrounded by wooden buildings. A serious fire could heat the ground enough to damage the pipes beneath, baking moisture out of the wood, causing it to crack and split. But the greater fire threat was simpler: pressure. Wooden pipes could handle the static pressure of water sitting in them. They could handle gentle domestic flow. What they could not handle was the sudden, violent demand of firefighting. When a hydrant opened, water rushed toward the opening with tremendous force. The pressure wave traveled backward through the mains, a shock wave moving at the speed of sound and water. Joints that had held for years suddenly separated. Weak spots that had never leaked suddenly burst. The very act of fighting fire could destroy the pipes carrying water to fight it. City engineers compensated by limiting hydrant flow. They installed valves that prevented full pressure discharge. But this meant less water on the fire, slower suppression, more buildings lost. There were other problems. Tree roots grew toward the water. Trees planted along streets could sense moisture seeping from leaky joints. The roots followed that moisture, forcing their way into joints, boring through the walls of the pipes themselves. A single compromised joint could drain an entire main. Frost heave lifted and shifted pipes during winter. Water in the soil froze, expanding as it became ice, lifting everything buried within it. Pipes laid perfectly level in summer rose and fell with the frost, misaligning joints. And the boring machines were crude. A pipe bored in 1800 might have walls that varied by an inch or more from one end to the other. Thick spots were harmless. Thin spots were time bombs. A thin spot might hold pressure for years, even decades. Then some shock, some vibration, some slight increase in flow would find that weakness. The pipe would burst with a sound like a gunshot. Maintenance crews worked constantly. Men with shovels and sensing rods walked the routes of buried mains, looking for wet spots, listening for the hiss of escaping water. When they found a leak, they dug. Sometimes they could tighten a joint with fresh iron bands. More often, they had to replace the entire section. It was brutal, continuous labor, and there was never enough of it to keep ahead of the decay. Yet despite all these problems, the wooden pipes persisted, and in many cases, they outlasted the engineers who doubted them. Here is the strange truth about wood buried in wet soil. It resists rot far better than wood exposed to air. The bacteria and fungi that break down wood need oxygen. Saturated soil contains very little oxygen. A wooden pipe buried below the water table sits in an anaerobic environment, starved of the agents that would destroy it. Elm, in particular, proved almost immortal under these conditions. The interlocking grain that made it so hard to bore also made it impervious to water penetration. Submerge elm in wet ground, and it will remain structurally sound for centuries. We know this because we have found the pipes. They are still intact. In 1968, a utility crew in downtown Boston was laying new sewer lines. What they found was a section of wooden main, still intact, buried 6 feet below street level. The pipe had been buried in the 1790s, nearly 200 years underground. And when the workers pulled it from the earth, the wood was dark but solid. The borehole was still perfectly round. The pipe was removed and sent to the Society for the Preservation of New England Antiquities, where it remains today. Similar discoveries have occurred in Philadelphia, New York, and dozens of smaller cities. Whenever construction penetrates deep enough, the wooden pipes emerge. In 2006, a utility crew in Philadelphia was replacing a water main on Chestnut Street, one of the oldest commercial streets in America. They expected to find what they usually found: iron pipe from the early 20th century, maybe some clay sewer lines from the 1890s, the usual archaeology of urban infrastructure. What they found instead was a section of wooden main, still intact, buried 8 feet below street level. The pipe was elm, bored to approximately 4 inches in diameter. Iron bands still encircled the joints, the metal corroded but recognizable. The wood itself was almost black, compressed by 2 centuries of soil pressure into something dense and hard. They called in archaeologists from the University of Pennsylvania, who documented the find, took samples for analysis, and determined that the pipe dated to roughly 1801. It was part of the original Latrobe water system, the very first centralized water supply the city had ever known. The borehole was still smooth, the marks of the auger still visible on the walls. The taper joints were still snug, fitted together as tightly as the day they were driven. 205 years underground, and the pipe was ready for service. New York has documented dozens of discoveries in Lower Manhattan, some dating to the Dutch colonial period when the city was still called New Amsterdam. Construction workers building subway lines, laying fiber optic cables, repairing sewer mains, all of them have broken through into layers of history they never expected to find. The oldest confirmed find is a section of pipe recovered near City Hall Park, dated to approximately 1677. Think about that number, 1677. Before the American Revolution by a century, before George Washington was born, before the idea of the United States existed in anyone's mind. That is 347 years old as of this recording, nearly 3.5 centuries in the ground. And the wood, preserved in waterlogged soil beneath layers of pavement and foundations and subway tunnels, was still structurally sound when archaeologists extracted it. These discoveries force a certain humility on modern engineers. We think of wood as temporary. We think of it as weak, prone to rot, unsuitable for infrastructure meant to last. And yet here are pipes that have outlasted every iron main laid above them. Here are joints that have held for longer than the United States has existed. Here is infrastructure built by men, using hand tools and animal power. And it is still there, still recognizable, still occasionally functional. The archaeologists who study these pipes handle them with something approaching reverence. They understand what they are holding. Not just artifacts, not just curiosities. Evidence that our ancestors solved problems we struggle with today. Evidence that sometimes the old ways worked better than we assume. The question becomes unavoidable. If wooden pipes lasted this long, why did cities abandon them? The answer, as always, is technology. By the 1830s, American foundries had caught up to European capabilities. Furnaces designed for large castings came online. For the first time, engineers could order cast iron pipe in the lengths and diameters they needed. Cast iron was superior to wood in almost every way that mattered. Iron could withstand higher pressure. You could open a fire hydrant fully without fearing the main would burst. Iron did not need to stay wet. Iron joints could be made airtight with lead caulking. And iron required less maintenance. A properly laid cast iron main could run for 50 years without intervention. Wooden pipes demanded constant attention. The transition happened gradually. New construction used iron. Old wooden mains remained in service until they failed. When they failed, iron replaced them. Philadelphia abandoned its wooden mains by the 1850s. New York followed. Boston converted in stages throughout the mid-19th century. But the cities did not remove the old wooden pipes. Why would they? Excavating every street where wooden mains had been buried would cost a fortune. The pipes were not in the way. They lay deep, below the level where new utilities would run, and so the cities simply left them. New iron mains went in above the wooden ones. The wooden pipes remained where they had always been, slowly settling deeper into the earth, filling with silt, forgotten. 100 years passed, then 200. Cities expanded upward. Skyscrapers rose on foundations that somehow missed the old mains by inches. Subway tunnels bored through rock that engineers never suspected was laced with hollowed logs. And occasionally, construction broke through. A backhoe bucket would strike something that shouldn't be there, and up from the darkness would come a length of blackened wood. Each time, the same amazement, the same recognition that the men who built these systems knew something we have forgotten. The contrast with modern infrastructure is uncomfortable to contemplate. Cast iron mains from the early 20th century are failing throughout American cities right now. Pipes laid in the 1920s and 1930s considered permanent at the time, are cracking, leaking, contaminating water supplies with rust and sediment. The infrastructure that was supposed to last forever is falling apart within living memory. New York's water system loses an estimated 1 billion gallons per day to leaks. Not per year, per day. 1 billion gallons of treated, purified water lost to cracks and failures in mains that are less than a century old. Philadelphia faces the same crisis. Boston, Chicago, every major American city. The pipes are failing faster than anyone can replace them. The money is not there. The workers are not there. The political will to dig up every street and replace every main does not exist. And beneath all of it, beneath the iron that is crumbling, beneath the concrete that is cracking, the wooden pipes remain. Not functional, not connected to any living system, but present, intact. Testimony to builders who worked with what they had and built better than they knew. What can we learn from this? Perhaps nothing practical. We are not going to return to wooden water pipes. Modern cities need systems that would destroy any bored log within hours. But we can learn something about durability, about matching materials to conditions, about building with the expectation that someone will find your work 2 centuries from now. The men who bored those logs did not expect them to last forever. They expected them to last long enough. That something better came in the form of iron and later steel. But the wooden pipes outlasted the iron. They will probably outlast the steel. Beneath the streets of Philadelphia, Boston, and New York, there are water pipes made of wood. Hollowed out tree trunks, bored by hand, joined with iron bands, buried and forgotten. Some laid before the Revolution, some serving water to firefighters who tried to save buildings from flames, some carrying the first clean water that tenement children ever drank. Those pipes are still there. They will still be there long after we are gone. Next time you walk through one of the old cities, remember what lies beneath your feet. Remember the men who felled trees and dragged them through mud. Remember the borers who cranked their machines hour after hour until their arms burned. Remember the trenchers who dug through frozen ground, the pipe layers who drove joints together with wooden mallets, the maintenance crews who walked the mains listening for leaks. Remember that the infrastructure we depend on began with trees, hollowed out logs buried in darkness, carrying water to people who had never had clean water before. And remember that somewhere beneath you, if you dig deep enough, you might still find them. Dark and dense and waiting. The first pipes. The forgotten mains. The wood that carried water before iron, before steel, before anything we now consider modern. They are still down there. In Philadelphia, where Latrobe first proved the concept would work. In Boston, where the oldest American water systems took shape. In New York, where Dutch settlers first buried hollowed logs beneath what would become the greatest city in the Western Hemisphere. The wooden pipes do not know they have been abandoned. They do not know that iron replaced them, that steel replaced iron, that plastic and composite materials now carry the water that once flowed through their bores. They simply wait in the darkness, preserved by the same wet soil that they were designed to serve. They built with what they had, and what they built endures. That is the story of wooden water pipes. The story of how American cities first tamed water. The story of logs buried in darkness, doing work we no longer remember, lasting longer than anyone ever predicted. If you made it this far, you understand why these stories matter. The forgotten trades, the buried infrastructure, the work that built everything we now take for granted. Subscribe if you want to see more. I will keep finding them, and I will keep bringing them to you. Until next time.